In this video, we're going to learn about variability, how to calculate sample variance, how to calculate sample standard deviation, and how to calculate the range of scores. It's very important that we understand how dispersed or variable our scores are in our data set. Having a measure of central tendency like the mean, median, and mode doesn't tell us everything we need to know about our set of data. Whenever we want to describe a set of data, we need to have at least one measure of central tendency and one measure of dispersion. That's why you will often see in journal articles, research reports, and research presentations, people will say the mean of the scores was 25.00 and the standard deviation was 5.00. If you haven't already done so, I would encourage you to watch my video on understanding variability. In most statistics books, I think they do a good job in explaining variability, but not so good a job helping students calculate measures of variability, particularly sample standard deviation and variance. What I'd like to do first is look at a definition of variability. A good place to start is by looking at the definition of variability, also called dispersion. Your book provides us a pretty good definition of variability. Variability can be defined as the degree to which individual scores are distributed around the mean. And of course, we're referring to the sample mean because we're dealing with sample data. Now let's take a look at that visually. If we were to draw a distribution of scores, and this one here almost looks normally distributed, the mean would be somewhere in the middle, and let's say the mean was equal to 75. And it really doesn't matter what these scores represent, but we have a distribution of scores and a mean of 75. What we're looking at in a measure of variability is how far any individual score, say here, is from the mean. Now some scores will be farther away from the mean than other scores. So when we look at variability or dispersion, we're trying to get a sense of how different or similar the scores are on average to the mean and one another. What's interesting is that if you have a distribution of scores that is tall and skinny, what that would mean is that most of the scores are very similar to one another and very similar to the average score. So this would be an example of something where there is little dispersion or little variability. However, if we had a set of scores where the distribution was short and fat, that would mean that there is a lot of dispersion or a lot of variability. In other words, the scores are very different from one another and the mean. the next thing we're going to look at is how we might calculate a value that could tell us how far on average a score is from the mean, any score. So we've taken a look at what dispersion or variability means. It's simply looking at how similar or different the scores are from one another. And it's important that we understand that, because knowing what the mean is, or the median or the mode, doesn't tell us everything we need to know about that distribution of scores. So what one might do to look at how different the scores are is they might take each score in the distribution and subtract the average score. So let's say, for example, you had a mean of 75 and you had an x sub I of 70, that value would equal 50. What one might do to get a value that could represent dispersion, one might think to take the mean, the average score, and subtract the score, because that would tell us how far this x sub I is from this mean. So for example, you could take a sample mean of 75 and subtract an x sub I of 70, and that would give you a value of 5. So in this case, the sample mean of 75 minus 70 would equal 5, and that would tell you how far this score is away from the mean. Or let's say you had a score of 80, and again that would be 5 points away. But notice that this score is below the mean and this score is above the mean. The problem, if we were to calculate the difference between each x sub I and each sample mean, or each x sub I in the distribution and its corresponding sample mean, is that if you sum them all up, you would get a value very, 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 very close to a value of 0. And the reason why is because half the scores are going to be above the mean, or half the scores are going to be below the mean. So if you were to take the sum of the quantity x, the sample mean minus x sub I, that is, you were to sum the quantity, the sample mean minus x sub I, you would get 0, because some of the scores are below the mean, some of the scores are above the mean. So what that would tell you is that there's no dispersion. Every score is the mean, or every score is exactly like the mean, and that may not necessarily be true. So if you have a distribution of scores, taking the sum of the quantity x bar minus x sub I would not tell you how dispersed or variable your scores are, because you would always end up with a value of 0. So because we can't just sum up the quantity x sub I minus x bar, we have to have a better way to calculate a measure of dispersion. And there are 3 measures of dispersion that are commonly used: the range, standard deviation, and variance. So let's say, for example, we had our 10 BMI scores: 18, 20, 20, 23, 23, 24, 24, 27, 33, and 36. And you can follow along. So we have 10 scores. We could calculate the range simply by taking the lowest score and subtracting it from the highest score. So in this case we'd have 18 minus 36, or our range would equal 18. And of course we circle our final answer. The problem with the range is it doesn't really tell us whether we have a lot of variability or a little variability, because it's simply looking at the difference between the highest score in the distribution and the lowest score in the distribution. So we know now that there's 18 units or 18-point difference in the scores. Obviously, the smaller the number, the lower the variability. The larger the number, the greater the variability. But it doesn't really give us a sense of, in units, how far the scores are from one another. The most common measure of variability is called standard deviation. And because we are going to calculate it on sample data, we're going to be calculating the sample standard deviation. That is going to be an estimate of the population standard deviation. Remember, there is a value of how dispersed or variable the scores are in the entire population. We don't know what that is, although there is a value. We can estimate it by calculating the sample standard deviation. That will be an estimate of phi, the population standard deviation. It could be a good estimate or it could be a poor estimate. To calculate that measure of sample standard deviation is fairly straightforward. Sample standard deviation will be equal to the square root of the sum of the quantity x sub I minus x bar squared divided by the sample size minus 1. Now, there are several formulas you will see to calculate sample standard deviation. This one I found is the simplest and most accurate for students to calculate. It's also one that's very easy to figure out how the calculation is working. So now I'm going to show you how to calculate the sample standard deviation. Remember, the formula for calculating the sample standard deviation is the square root of the sum of the quantity x bar minus x sub I squared divided by n minus 1, where n equals your sample size or the number of data points that you have. Remember, calculate these statistics as I show you how to do them. So what I like to do is I will first make a column of all of my x sub i's. Notice that I'm going to stay nice and neat as I go and do this. So I'm going to do this in my ordered data. In this example, I'm going to use the 10 BMI scores. So I'm going to have 18, and then I have 20, and then 20, and then 23, and then I have 23, and then I have 24, 24, 27, 33, and 36. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Always go back and make sure that you have the total number of scores that you need. The next thing I'm going to do is make a second column, and that column is going to represent my sample mean. And I'm going to put that next to each one of my x sub i's. Well, to calculate the sample mean, you'll remember the sample mean is equal to the sum of the x sub i's over n. So what we can do here is we can sum up or make this row a row of sums. So if we sum up all of the x sub i's, that is, we add them up, we'll end up with 248. So we can plug that into our formula here. 248 divided by 10 would equal 24.80. So now what I would do is, in this column, I'll write in 24.80 next to every one of my x sub i's. I know it seems redundant, but it'll help you later on. So I'll go ahead and write 24.80. And then next to here, 24.80. And then 24.80, 24.80, 24.80, 24.80, 24.80. Hopefully your penmanship is better than mine with this tablet here. And 24.80, and then finally 24.80. So what I've done so far, I've made a column of my x sub i's. I calculated the sum of the x sub i's because I needed to get the sample mean for this set of scores. The sample mean is equal to the sum of the x sub i's over n, and that would equal 24.80. The next thing I'm going to do, the third step, is I'm going to make a column of the quantity x sub I minus x bar, or a better way to think about it is, the quantity x sub or x bar minus x sub I. So let me draw that for you. So label this x bar minus x sub I. So now I'm going to make this third column that's going to represent the quantity x bar minus x sub I. So if I take my 24.80 and I subtract 18, that's going to give me negative 6.80. And then 20 minus 24.80 is a negative 4.80. And then 20 minus 24.80 is a negative 4.80. 23 minus 24.80 is a negative 1.80. Again, 23 minus 24.80 is a negative 1.80. 24 minus 24.80 is a negative 0.80. Again, 24 minus 24.80 is a negative 0.80. 27 minus 24.80 is 2.20. 33 minus 24.80 is 8.20. And then finally 36 minus 24.80 is 11.20. Now, because some of these scores are below the mean, you're going to get negative values here, and then the scores that are above the mean, you're going to get positive values. But if you were to sum up the quantity x bar minus x sub I, you should get 0. Because the negative scores, the scores that represent scores that are below the mean, will cancel out the scores that are above the mean. This is always a good check for you to do to make sure your arithmetic is okay. I would encourage you to do this at least twice. Now, sometimes what will happen is because we have rounding error here, notice I'm only carrying these out 2 decimal places. I'm only doing that because in the program that I'm using to teach you this doesn't have a lot of room here. But I would recommend you carry out all of your values 3 decimal places, and that will keep you from having this rounding error. as long as the leading digit is 0, you'll be fine. So if you ended up with something that was like 0.10, you're more likely going to be okay. If this value was 1 or 0.90, then I'd go back and check your math in here again. But always sum these up to make sure your math is okay for 0. The next column I'm going to make is I'm going to make this fourth column, and that's going to represent the quantity x bar minus x sub I squared. So in other words, I'm going to take this value here and I'm going to square it. Now remember what your third grade teacher taught you, that if you square a negative value, you will always end up with a positive value. So if I take negative 6.80 and I square it, I'll get 46.24. If I take 4.80 and square it, I get 23.04. Again, 4.80 squared is 23.04. Negative 1.80 squared is 3.24. Again, negative 1.80 squared is 3.24. Negative 0.80 squared is 0.64. Again, negative 0.80 squared is 0.64. 2.20 squared is 4.84. 8.20 squared is 67.24. And finally, 11.20 squared is 125.44. And you're going to want to get the sum of the quantity x bar minus x sub I squared. So go ahead and sum up all of these values. So if you take the sum of the quantity x bar minus x sub I squared, you'll end up with 297.601. So what I would do is make sure you're carrying out all of these at least 3 digits. I've just done it here just to demonstrate. Now you can plug your values into this formula here. So let's go ahead and do the work. I'll show our formula. Sample standard deviation is equal to the sum of the quantity x bar minus x sub I squared over n minus 1. So now we'll plug in our values. Remember to keep using the square root sign. So the sum of the quantity x bar minus x sub I squared is right here because we calculated it already. So we'll put in 297.601, and that will be divided by n. That's the number of data points you have, sample size, number of subjects you have. You can see that's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, minus 1. We'll keep showing our work each and every step. So that's 297.601 divided by 9. We keep going. Remember, don't forget your square root sign. You'll end up with 33.06, and the square root of 33.06 is 5.75. And as always, we circle our final answer carried out 2 decimal places. So the sample standard deviation of this set of scores is 5.75. Now let's talk about what this means. What this value represents is values that were calculated from these units. And remember, these units are BMI points. So these are BMI scores, body mass index scores. So what this value means is that on average, any score in this distribution of scores is about 5.75 BMI points away from the mean. Now, some of the scores are going to be below the mean, some of the scores are going to be above the mean, but on average, a score would be about 5.75 units or BMI points away from the mean. The good thing about the standard deviation is it's interpretable. That is, the value represents whatever unit of measurement the x sub i's represent. So if these were seconds, this would represent 5.75 seconds. If this were pounds, if these scores were pounds, this would represent 5.75 pounds. If, let's say, for example, this was dollars, this would represent $5.75. So the good thing about standard deviation is that it's interpretable in terms of the unit of measurement in which it came from. Now, one thing you always want to do is compare the variance to the standard deviation. So relative to a mean of 24.80, we can see that any individual score would be about 5.75 BMI points away from that mean. What this tells us is that there is some moderate variability going on. Let's just imagine for a moment that the variance was 0. What that would mean is that every score, regardless of the mean, is exactly the same. There's no variability whatsoever. Now let's imagine that the sample standard deviation was 1. What that would tell us is that there's very little variability. That is, on average, the BMI scores are only 1 point away from the mean. So we can see here we have quite a bit of variability. That is, the BMI scores in this set of scores are different from one another. Now that we've learned how to calculate the sample standard deviation, let's take a look at how to calculate variance. Now, variance is another measure of dispersion or variability, but the difficulty with a measure of variance is that variance is not calculated from the same units which it came from. So what will end up happening is you'll get a value that is not interpretable because it's not, let's say, 10 units. It's not $11 or 75 pounds. It's just a measure of how different the scores are from one another. The formula for calculating variance is as follows. The formula for calculating variance is the sum of the quantity x bar minus x sub I squared over n minus 1. So what we could do is we could go through and we could do the same thing we did before. We could make a column of x sub i's. We could make a column of x bars. We could make a column of the quantity x bar minus x sub I. And finally, we could make that last column we made, which was the sum of the quantity x bar minus x sub I squared. And then what would happen is we would get the sum of the value of x bar minus x sub I squared, and then we could plug that into our formula. So let's just say this was 40. And let's say we had 10 scores. So it would simply be 40 over 10, or our variance would be equal to 4. The problem with this is that it's just an overall measure of variability. But notice that we could have done something else besides calculating it using the formula. What we could have done, instead of doing all of this work, is simply taking our value that we got from our calculation on standard deviation, which was the sum of the quantity x bar minus x sub I squared over n minus 1. And notice how these are almost identical. The difference is the square root. So what I want you to remember is that standard deviation is simply the square root of variance. This is not phi squared. This is the symbol for variance, and this is the symbol for standard deviation. So if you take, in terms of your sample, if you want to calculate standard deviation, just take the square root of variance. Now, if you want to know variance, simply take your standard deviation and square it, and that will give you variance. Again, the problem with variance is that it's uninterpretable. Although it is a measure of dispersion, that is, the larger the value, the more variability you have, the smaller the value, the less variability you have, it's not calculated in the units from which it came from. The majority of the time, you are going to be reporting the mean as well as your standard deviation. And if you have the sample mean of a distribution of scores and you have the sample standard deviation of that distribution of scores, you will know everything there is to know about that distribution. Again, if you know the variability of the scores and you know the sample standard deviation of the scores, you will know everything there is to know about that entire distribution of scores. So oftentimes you will see that is that people will report the sample mean as well as the sample standard deviation. That lets us know everything there is to know about that entire distribution of scores. What I'm going to do now is go through another calculation for you, calculating sample standard deviation and variance. Let's go ahead and do another example of calculating the sample mean and the sample standard deviation. The scores we're going to use in this example are scores from a self-esteem assessment where we had 8 patients from an anorexia treatment facility complete a self-esteem questionnaire to measure their self-esteem. The higher the score, the more self-esteem they have. And here are the scores. 15, 15, 15, 20, 20, 21, 25, and 36. So 15, 15, 15, 20, 20, 21, 25, and 36. We have 8 scores. Remember, the formula for calculating sample standard deviation is the square root of the quantity x sub I minus x bar squared over n minus 1. So again, the formula for calculating sample standard deviation is the square root of the sum of the quantity x sub I minus x bar squared over n minus 1. Now, we also want to calculate the sample mean, which will be equal to the sum of the x sub i's over the sample size. The first step is to go ahead and create a column of all of your x sub i's. And you can follow along on your paper. So the first x sub I is 15, then we have 15, and then 15, then we have 20, 20, 21, 25, and 36. 1, 2, 3, 4, 5, 6, 7, 8. Then what we need to do is go ahead and get our row of our sums. So if we sum up all of the x sub i's, we'll get 167. Now we can calculate our sample mean. The sample mean is equal to the sum of the x sub i's over n, or 167 divided by 8, which will give us 20.87. Now what we need to do is make a column of our sample mean, or x bar. Again, we're going to write this in next to every one of them. So we'll have 20.87, and then again 20.87, and you can follow along. And then 20.87, 20.87, 20.87. Don't just write ditto signs, you want to put in the values. 20.87, 20.87, and 20.87. Hopefully you're writing much neater than I am. Now that we have the column of all of our sample means, we'll go ahead and put in a column that'll represent the quantity x sub I minus x bar. That is, we're going to take each x sub I, subtract the sample mean, and put that value right here. So if we take 15 and we subtract 20.87, we're going to get a negative 5.87. 15 minus 20.87 again is 5.87. 15 minus 20.87 is a negative 5.87. 20 minus 20.87 is a negative 0.87. 20 minus 20.87 is a negative 0.87. 21 minus 20.87 is 0.13. 25 minus 20.87 is 4.13. And 36 minus 20.87 is 15.13. And again, you want to sum up all of these values just for a check of your math. You should get 0. Now let's make another column of the quantity x sub I minus x bar squared. So we're going to take each value here and square it. So if we take a negative 5.87 and square it, we'll get 34.44. And again, negative 0.587 times negative 5.87 is 34.44. And again, 34.44. And then negative 0.87 squared is 0.75. Again, negative 0.87 squared is 0.75. 0.13 squared is 0.016. 4.13 squared is 17.05. And 15.13 squared is 228.91. Again, I would suggest that you might carry all of these values out 3 decimal places just so you don't have lots of rounding error. Now you want to get the sum of the quantity x sub I minus x bar squared. So you want to get the sum of the quantity x sub I minus x bar squared. So you're going to sum up all these values, and if you do that, you will get 350.79. Now we can plug these values now into our formula. So again, we're going to show all of our work. The sample standard deviation is equal to the sum of the quantity x sub I minus x bar squared divided by n minus 1. So we'll put in our sum here of the quantity x sub I minus x bar squared. It's right here. So let's go ahead and put in 350.79 divided by n minus 1. So we've got 8 minus 1 would equal 7. Keep showing our work. We'll end up with 50.11. or the square root of 50.11 is 7.0791, but we're going to round it to two significant digits, which will be 7.08. So what this tells us is that on average, the participants in this distribution are about 7 self-esteem points away from the mean. And if we look at that in relationship to the mean here, that tells us that there's quite a bit of variability. That is, not everybody has the same self-esteem score. As always, if you have any questions, make sure you stop by during office hours. Have a great day.